Okay, guys, so in this video, we start with um, this proposition that is gonna be very important for us to describe the integers mode n. Okay, so let C to the n be the set of equivalence classes of the integers mod n and a, b, c elements of C to the n. Okay. So the following is true. Addition and multiplication, our regular addition and multiplication are commutative. So that means A plus B is congruent to B plus A mod n. And A times B is congruent to B times A mod n. Okay. Also, this is easy to prove, right? We will discuss very fast these proofs. Addition and multiplication are associative. That means A plus B plus C is congruent to A plus B plus C mod n. And A times B times C is equivalent to A times BC mod n. 3. There are both additive and multiplicative identities. So that means A plus 0 is congruent to A mod n, and A times 1 is congruent to A mod n. Number 4, multiplication distributes over addition. So what does it mean? That E times B plus C equals A times B plus A times C mod n. So notice that all this is regular adding and multiplication, okay? But we're not defining anything new here, really. So next one, for every integer a, there is an additive inverse minus a. And that means a plus minus a is equivalent to 0 or congruent 0 mod n. And 6. So let a be a non-zero integer. Then the greatest common divisor between a and n equals 1 if and only if there exists a multiplicative inverse b for a mod n. That is a non-zero integer b such that a times b is congruent 1 mod n. Okay, so let's discuss some of this. So what does it mean a plus b congruent b plus a mod n? So this is, remember that we said before that we put it like this. We said that a is congruent b mod n if and only if there exists case such that n times k equals a minus b, or what we said before, n divides a minus b, remember? So that means if I subtract these two guys, this is trivial because a plus b minus b plus a, that's equal 0, right? Because they're integers. So this 0, so any k will do it, right? So this is a minus b so let's see. A is congruent b, so this guy, so this guy is congruent to this guy, right? If only if exists k such that n times k equals a minus b, right? So in this case, I have what? A minus b is 0. So this is my a minus b, right? And this is equals n times 0, right? So that's my k. K equals 0. I wonder if k can be 0. Well, let's do another one. So this one will be the same thing. AB minus BA is equals to 0, right? So again, k has to be 0. So this equals n times k, n times 0. Okay. Okay, let me check. I think k can be 0. I will check. Well, let me check in a second. Yeah, so k can be 0. The one that cannot be 0 is the one dividing. So this n is the one that cannot be 0. Okay, so the number one is ready. So the same thing here, right? Because at the integral level, these two guys are the same, right? So when you subtract them, it gives you 0. So the same thing here, you subtract them, they give you 0 because at the integral level, they give you the same thing. So same thing here, same thing here. All these properties are coming from the integer. So all this is true too. This is true too, right? And then this one is probably the most, the only interesting one. Okay. Okay, so let me give you 2 minutes to try this. So let a be a non-zero integer. Then the greatest common divisor between a and n is 1, if and only if there is a multiplicative inverse b for a mod n. That is a non-zero integer b such that a times b congruent 1 mod n. Okay. So let's work on it. So let's see. Let me give you 2 minutes to start. Okay. So let's try first. Let b an uncertainty, then. So maybe probably this one is easier to start with. All right. So try that one first, and then the other one. I probably have to define the greatest common divisor. So this is a theorem. So let me define remember the theorem, okay? I don't think we covered that. So theorem, let a and b non-zero integers. Then there exist integers r and s such that the greatest common divisor of a and b equals ar plus bs. Yes, and furthermore, the greatest common divisor of A and B is unique. I think with that we have enough, right? So yeah, so let's do the easiest ones. That is this direction. Oops. So it's saying there exists a multiplicative inverse B for A mod N. So assume, so we're gonna prove that if A times B comes with 1 mod N, then we must have the greatest common divisor between A and N equals 1. So let's assume this. That means A has an inverse called B, right? So by definition of mod N, N must be divided AB minus 1. That means there exists K integers such that NK equals AB minus 1. Or we can rewrite like this, 1 equals AB minus NK. So let D equals the greatest common divisor of AN. We don't know that the greatest common divisor is 1, right? But let D be equals this. So that's what we know we want to show. Greatest common divisor of N. So just that's what we're going to prove, right? Greatest common divisor of N equals 1. But from here we see, from a star, we see that the following. So from here, well, no, better from here. Since this is the greatest since this is the greatest common divisor of A and N, D, let's put it like that. D divides A and D divides N, right? So we see that D divides A and D divides N. That's part of the definition of being the greatest common divisor, right? But notice this. If D divides A and D divides N, then by star, D divides 1, right? But the only number that divides 1 is 1. So therefore, D equals 1. Okay. So it gives me a little trouble this last part, to be honest. So I prove it myself. I like to do my own proofs. So I was doing the video and I said something is weird. Something's weird. I don't like it. I was trying to use this theorem. But then, yeah, so I had to kind of check the book, and this part was the right way to conclude this part. For the other one, I didn't have any problem. So let's do it. So it says that if the greatest common divisor of A and N is 1, then there exists inverse B such that A times B equals 1 mod N. Okay. So assume the greatest common divisor of A and N is 1. So by theorem, by this theorem over here, there exists R and S, right? Such that this is true. Okay, 1 equals A times R and S, because this is the greatest common divisor of A N, right? So this is equals to 1, so the greatest common divisor is AS plus BS. In that case, this is equals to 1, okay? So this is GCD AN. Okay. So now I modify a little bit. So uh, ns equals 1 minus AR, and then I can, for convenience, I multiply times minus 1. So I get n times minus A equals AR minus 1. And that implies that AR is congruent 1 module N. Okay. Therefore, R is the multiplicative inverse of A. Okay. Letting be, and this part also is from the book. Okay. It's important. I think the book is correct. Letting B the equivalent class of R, AB is congruent to 1 modulo N. So since I found an R, right? I found an R on the integers, right? R belongs to, so here R and S are integers, but I need the R on Cn, okay? So, I need to say this. Letting B be the equivalent class of R, then A times B congruent 1 mod N. Okay? So yeah, those greatest common divisor always make me check because I think I can easily make mistakes for some reason. I think I have a more analysis mind than an algebraic mind. Okay? Okay, so this is the end of this proposition.